Hello everyone, my name is Chunhua Shen. I'm going to talk about some recent work on explainable deep few-shot anomaly detection using a method we call it deviation networks. So the majority of this work was done by my colleague Dr. Guansheng Pang and my PhD student Choubo Ding. So first I will present some background about the anomaly detection, especially like few-shot anomaly detection, which means we have access to a large set of unlabeled data. At the same time, we do have a small set of labeled data, and why this problem is interesting. And then I will describe the proposed approach, deviation network, and last, I'm going to show some of the numerical results. So, okay, just a few words about anomaly detection. So, anomalies are referred to as data points that differ significantly from most of the majority of the data in a data set, and they are often rarely and irregularly distributed in the data space, right? Such as the colored points on the right figure. The task of anomaly detection is to assign an anomaly score to each data point and return anomaly ranking of the data points based on this anomaly score. So basically we need to learn a mapping function which takes the data points as the input and then return a score. So pretty much the same as classification or regression. The research problem on anomaly detection is of interest because it has a large number of downstream applications in different domains, such as, for example, here I show some of the examples like detection of cyber attacks and malicious social network accounts, criminal activities in videos, which has a lot of application in video surveillance, and of course also like financial crimes detection, disease diagnosis, and the defect detection in industry. So the task of anomaly detection is not new. It actually has been studied for the past quite a few years. But however, anomaly detection is notoriously challenging. One of the challenges is the heterogeneity among anomalies. That is, different anomalies may exhibit completely different expressions. For example, here, just check the figure here. So, like accidents, robbery, and explosion events in some video surveillance footages, right? And also, because of the problem, the anomaly being irregular, anomalies remain unknown until they actually occur in most of the cases. So as a result, it is very difficult, if not impossible, to collect the positive anomaly data covering all kinds of anomaly. And that's probably the reason why in the literature most of the anomaly detection methods are actually unsupervised, simply because it's very difficult to collect all of the positive labeled data. So yeah, most of the methods in the literature are unsupervised, and there are also some semi-supervised learning methods, just using a small subset of labeled data. This is really to avoid the requirement of labeling a lot of anomaly data. It's very difficult to collect such data. In the literature, some methods attempted to use like a small, to use some kind of weakly labeled information. So in the setting of weakly supervised learning framework. Right? For example, we can use a small set of partially labeled anomaly data plus a lot of unlabeled data to train a model. Earlier this year, we published a survey paper in SCM Computing Survey, which covers most of the typical methods in the literature. In this work, we consider the problem of anomaly detection with few short, partially labeled anomaly data. So, in other words, in addition to the availability of a large-scale normal data set, as in the like a semi-supervised setting, we are also given a small set of labeled anomalies that only partially cover the classes of anomaly. Within, ARM to learn anomaly scoring function, phi, and this is a problem commonly encountered in many important applications. For this particular problem, there are a few challenges. For example, the first challenge is, the few-shot anomaly data may contain samples drawn from diverse anomaly classes of dissimilar class structures. And this can lead to, great difficulty of learning a good representation of the anomaly data space. And also, the second challenge is because we can only access to a very small number of the anomaly classes, anomaly categories. So there can be, infinite number of other anomaly classes unseen in the training. And how can we take this unseen anomaly categories of data into consideration? That's a big challenge. And of course, as many other machine learning algorithms, the data we have access to might be noisy, which means some of the labeled anomaly classes may be actually from the normal data. And when we need to make the algorithm robust to this kind of noise. So the existing solutions in the literature mainly are unsupervised approaches and semi-supervised approaches. And those two types of methods usually do not address the partially labeled data setting that we are trying to address here very well. Right? So, for example, the unsupervised methods do not have any knowledge about the the anomaly data. So those unsupervised methods just work on anomaly contaminated unlabeled data, and the methods do not use any manually labeled training data. And then the semi-supervised approach assume the availability of a small set of manually labeled normal training data, but they are no labeled anomaly data. So the setting here is we try to learn from those partially labeled few short anomaly examples to detect both seen and ideally unseen anomaly classes. Right? At the same time, we want the method to be robust to possible anomaly contamination in the normal data. In summary, we introduce a novel few-shot anomaly detection framework, and our methods use a limited number of anomaly examples to train the anomaly detection model without assuming the examples illustrating all of the possible classes of anomaly, which is simply not possible. And the proposed method fulfills a direct differentiable learning of anomaly scores. So, to the best of our knowledge, this might be the first framework for taking advantage of limited anomaly examples to achieve end-to-end anomaly score learning. And the results is significantly improved detecting accuracies along with accurate anomaly explanation. Last, we propose this novel anomaly detection model. We call it a deviation network, the method assumes Gaussian prior and z-score based deviation loss and multiple instance learning to learn robust and a robust model which can generalize well to the test data to detect both seen and unseen classes of anomaly. Our extensive experiments demonstrate that the proposed deviation network works quite well with different types of network backbones. Just show the flexibility of the network, and also the model achieves state-of-the-art performance in terms of detecting different types of anomalies. For example, texture and object anomalies in image or video data, and it significantly outperforms those compared methods by a large margin in terms of sample efficiency, robustness to anomaly contamination, and also in terms of the generalization capability to unseen anomalies. And the network also offer accurate anomaly localization for explanation of the detected anomalies. To our knowledge, this might be the first work that we can provide some sort of explanation, right? Because everybody knows that in deep learning, how do you interpret a trained deep model is still a open problem, right? Here we just try to for this particular anomaly detection task, we move one step further. And also the deviation network establishes this few-shot anomaly detection performance benchmarks on the publicly available real-world datasets from diverse anomaly detection applications. And in this way, we provide baselines for the development and evaluation of this new few-shot anomaly detection methods. Let's check the high-level idea of this proposed deviation network. So we first use an anomaly scoring network, which is a function, to output a scalar anomaly score for every image patch of a given image input X. So just check this plot. In this case, we use the anomaly detection in images as an example. Of course, the method itself is generic and it can be applied to other different types of data, for example, tabular data. Second, to guide the learning of anomaly scores, we then use a reference score generator to generate a scalar score, which is the we call it a reference score. It is defined as the mean of the anomaly scores for a set of randomly selected normal examples. In this plot, we denote this randomly selected set of normal examples as R, just on the left side of the figure. So the reference score is drawn from a prior probability F, and this basically enables us to efficiently generate the reference scores for the normal examples, and somehow it helps to achieve interpretable anomaly scores. Last, the samples, the mean and its associated standard deviation are then input to a multiple instance learning based deviation loss to guide the optimization. Then here each image is represented as a bag of image patches, and we aim to optimize the anomaly scores such that the scores of the anomaly bags should be statistically significantly deviate from the sampled normal examples in the uptail of the distribution, and at the same time having the scores of normal examples as close as possible to the sampled normal examples in the set R. And the use of this multiple instance learning based deviation loss enables the network model to learn more generalized representations than those holistic deviation loss, and this can lead to significantly reduced false detection errors, as we demonstrated in the experiment of our paper. So this is the overall pipeline of the proposed deviation network. This slide provides some details to each of the components in the deviation network pipeline. Here I just want to say a few more words about this this Gaussian prior based reference scores, because this is important, right, to the success of the network training. So a key problem here is to provide some type of knowledge to guide the optimization of the anomaly scores. To address these issues, the deviation network designed a module to generate a reference score. Here it's in this slide, it's denoted as mu r, which is defined as the mean of the anomaly scores of a set of some randomly selected normal examples. So this score is directly fed into the network output to guide the optimization of the function phi. And there are two possible approaches to generate this score, this reference score, either using data-driven or prior-driven approaches. So data-driven methods involve a model to learn this reference score based on some examples, and prior-driven methods generate this reference score from a chosen prior probability f. The prior-based approach is used here because the chosen prior allows us to achieve good interpretability of the predicted anomaly scores, and also it can generate this reference score constantly, and this can considerably more efficient than the data-driven approach. And in our work, we just assume Gaussian distribution for the anomaly scores. This is reported in a few papers, which shows that on most of the datasets, actually the anomaly score follow Gaussian distribution quite well. So in our case, we just define a Gaussian prior-based reference score. So the proposed deviation network is a deep neural network. So it is interesting if we can provide some kind of explanation after we train the model on the few shot dataset. Here we just take advantage of the published paper in computer vision. It's called GradCam, which can provide some kind of explanation in image classification. Here we just use this method because the proposed deviation network is end-to-end differentiable. We can easily calculate the gradients. With this method, it is possible to localize the anomaly regions in anomaly images. We carry out extensive experiments and try to answer some key questions. For example, we want to know how effective does this proposed deviation network leverage a few random labeled anomaly data, and how does the deviation network generalize to open set anomaly detection, and also we try to visualize the detected anomaly region of the the positive anomaly sample, right? We try to see the explanation, and also what is the contribution of each component of the deviation network to the overall performance, and we also did some experiments to find out the sample efficiency of the deviation network. And also last, because we aim to train a robust model, we want to know how robust is the deviation network with respect to different levels of anomaly noise contamination. This table just shows the key statistics of the image datasets. The first 15 datasets compose the MV-Tech anomaly detection dataset, and this table reports the AUC ROC metric of the deviation network, and also we compare our method with 5 recent methods, and as you can see, the deviation network achieves the best performance on 7 datasets out of 9 datasets, and it outperforms the best competing method by a large margin on 7 of the 9 datasets. So as a result, the proposed method achieves the best average AUC ROC score on these datasets. So the result here also confirms that our method can take advantage of those labeled anomaly data to achieve much better performance than those unsupervised methods, which is understandable because, of course, right, we are using more supervision signal to train the model. Unsupervised methods do not use any of the labeled data. This is a result for OpenSet in the OpenSet setting, and again, our method works the best compared with the methods in the literature. I'm not going to get into the details. This figure shows some visualization of the anomaly localization for 2 groups of images in our experiment. Here, the first row is the input image, and the second row is pixel level ground truth, the anomaly mask, and then the third row is the anomaly localization result of our method. And we provide two sets of the results. As you can see, the results here shows that the proposed deviation network can actually accurately localize anomaly pixels of different anomaly classes on different surfaces, and regardless of the size or shape of the anomaly regions, image regions. So this actually offers some kind of simple explanation of the detected anomaly class. we report the pixel level AUC ROC performance of the deviation network in anomaly localization here in this table. And compared with the three baseline methods, our proposed deviation network provide more accurate localization of the compared with the compared baseline methods. Those figures basically to just try to compare with baseline methods in terms of the sample efficiency, as we can see. So all of the four methods achieve better performance when the labeled anomaly data increase, right? Which is understandable. When you use more labeled data, of course, the performance in general will be better. But consistent with all the other results, the proposed deviation network is consistently performing better than the compared methods. We provided some aberration study in terms of the design of the deviation network. With for example different backbone networks. So I'm not going to get into the details. If anyone is interested, please refer to our published paper. And this is an experiment to show the results in terms of the noise level. Again, our method works quite well. And this is another experiment in terms of the top K. The K value in the multiple instance learning loss terms. We also did some experiments on the tabular data besides the image data, and our method works quite well as well. So to conclude, we consider this new few-shot anomaly detection problem and introduce a novel framework. We call it deviation network to tackle this task. And this is achieved by taking advantage of a few labeled anomalies with a Gaussian prior to implement this end-to-end differentiable learning of fine-grained anomaly scores. And by doing so, the deviation network can be trained more robustly with respect to anomaly contamination, and also more. We show that our network is more sample efficient. And in general, it can learn much better model to achieve improved accuracies. So I guess one of the key messages I want to deliver here is, if they are labeled anomaly examples, then for the task of anomaly detection, it is of great benefits to, exploit this labeled anomaly examples when you train a model to do anomaly detection. That's all. Thank you.